Alright, so last time we started talking about functions of random variables. So that's where we stopped last time. So let's start here with functions of random variables. Well, as we thought last time, that if we have a random variable x, like if we said that x, put it as a capital X, because you guys know capital X is a random variable and small x is the assigned value, the random variable. So if we said that x is a random variable, so any function of x, like let's say that y is any function of x, like for example, y is equal to x plus 2. This is still a random variable, okay? So like if you have a load on a beam and this load is a random variable, so the reactions are a random variable and the shear and the moments are all still random variables. So that's the thing that we need. And the same rules is going to be applied. Like if we said, like if we were talking about fy of y, and as we know that this is the CDF, or the cumulative function, then this means that the probability of our random variable y less than or equal to y. And if we draw a normal distribution, and this is y, so this is the fy of y. So if I substitute it with the function, this function, or let's say gx, that means that the probability of gx less than or equal y. How did I came with this? Because I have the y is the function of random variable x. Okay? Do you guys know the concept of inverse? Like, do you guys remember, like if we said that tan theta is equal to 5 theta. So what you do is to get the tan inverse of 5, right? So what is the inverse? The inverse is the image on x-axis. So it's not like, I want to say that, like if I want to find the inverse of gy, like let's say that y is equal to gx. So if you want to find x, it's going to be the g inverse of y. Let's put capital Y, a small one. The inverse, g inverse of y, is not 1 over gy. That's not true. Okay? So g inverse of y is the inverse of gy on the x-axis. Like for example, if you have y equal to x squared plus 2, the g inverse of y, actually is the x. And this should be equal to, you have to convert this function to x squared is going to be equal to y minus 2, and then x is going to be the root plus or minus y minus 2. That is the g inverse of y. Okay? So the image on the image of function gy on the x-axis. So you can say here that the probability of x is going to be less than or equal to g inverse y. How did I came up with this? I take inverse for both sides. The inverse of this function is going to be x, and the inverse of this function is going to be g inverse y. So that is what we have here. So as we know that fy, that means the probability of y is less than or equal y. This is the same thing. You can, since you have the probability of x less than function, less than this function, you can say that this is fx of g inverse y. So fy of y is going to be equal to the fx of g inverse y. So this is how we prove it, because fy is the probability of y. So if you have a probability of x, that means that this is fx of this variable. And if you guys remember, if we want to find the BF from the CDF, we have to differentiate the F capital to the F small. So if we differentiated this with respect to y, so this is going to be Fy of y, and this is going to be, you have to differentiate this function. But I want to put this in example before I move forward. Okay, let me put it here, and then I'm going to put the example after. Okay, so if I differentiated this with y, but let me revise something very quick with you about differentiation before I do this. So let's say that we have y is equal to x squared plus 2 all to the power 3. And I ask you to find the derivative with respect, let's say with respect to z, any variable. I want to differentiate this function with respect to a completely different variable from x and y. What would be the derivative? So you have to differentiate both sides with respect to z. So what is the differentiation of y?
0.
Not 0.
It's
gonna be, it's a variable, dy dz, right? Because y may be function in z, we don't know, okay? So it's gonna be dy dz. How about the derivative of this function? So first you have to differentiate this function with respect to x, and then like, okay, let's say you do this differentiation. With 3 is gonna be 3 here, and you're gonna have x squared here, plus 2 all to the power 2 multiplied by 2x multiplied by
dx by dz.
dx dz, right?
Yeah.
So first you differentiated this function with respect to its own variable, and at the end I differentiated with dx dz, right? Okay, so what happens here? Look at this function. This function is function in y. So if you differentiate with respect to dy from the basics that we learned, it's going to be the f small y without dy dz. Why? Because this is function already in y, not function in any other variable. But this one is function in x, and we are going to differentiate it with respect to y. So this is going to be fx small g inverse y multiplied by the derivative of this function with respect to y. So you have to get d dy to this function, g inverse y. I'm gonna put it in an example right now so that we can understand it better, okay? So let's say, example. And this example is going to be, I'm going to assume that the function of the random variable is monotonic. Monotonic, that means it either increase or decrease. It doesn't go up and down, okay? It only increases or decreases. So let's say I have here assume that gx is a monotonic function. So let's say y equal gx, and this is monotonic function. And let's say this is y, this is x, and our function is something like this. It's increasing. There is no decrease. Let's say this is y equals gx. So what we are doing here is that, I'm gonna put it here, monotonic. And you have x as a random variable. Like, let's say this is the distribution of x. And definitely y is going to be a random variable. I'm going to put here, this is dfx of x, right? I put it like here. This is how x is changing. So definitely y is going to be a random variable. So this is going to be also something like this. And this is fy of y, all right? So let's pick a point on this curve, let's say I'm gonna pick this point. Right, and I'm gonna make something like this and something like this. So this is going to be x, and this is y, and our function is y equal to gx. So this is y is going to be equal to gx, and x, as we got it, like if you want to find x is the g inverse of y. So you can write it both ways, g inverse of y. Okay. So if you want to find the probability density function, so you have to come here, and then this is the fx of x, which is the fx of g inverse y. On the other hand, on this curve, this is the probability fy of y. You can write it like this. Okay, so we can do it that way, the same way that we have done it here. You can say that fy of y, which is this part, that means that what is the probability of your random variable to be less than or equal to y. And that is the same thing, because y is equal to gx, you can say that the probability of gx is going to be less than or equal y, and also this is the same thing like saying the probability of your x is less than or equal g inverse of x. So this is supposed to be like this. I mean, like, should be equaling value. Sorry, this is g inverse y. All right, so, and we just said that this means the fx. When you say the probability of x, that means this is equal to fx of g inverse y. All right. So then we start talking about the f small. So if you want to find f small, you need to take the derivative. So the fy of y is going to be equal to d dy of the fy of y, right? So we need to take the derivative of this function, and this is supposed to be equal to d dy of fx, because right now what I'm doing here, I want to prove that the fy of y is equal to the fx of g inverse y. And from this, I want to find out what is the BDF. So this is the CDF, and I want to find what is the BDF. This is the BDF. So I take the derivative of fy of y, and then I know that this is equal to fx of g inverse y. So if I took the derivative of this with respect to fx, this is going to give me fx small, and then this is going to stay the same, g inverse y, and I need to take the derivative of what is inside the bracket. So this is going to be equal d dy of this, g inverse y. And by the way, g inverse y is the x. Like, I can remove it, g inverse y, or I can write it one more time here, fx g inverse y, and this is dx dy. This is the same like this, because we know that g inverse y is equal to x. All right, so this is the rule that we want to prove here, that the BDF of y is equal to the BDF of x multiplied by the differentiation of x with respect to y if your function is monotonic, like it's only increasing and have only one root. It's supposed to be monotonic. We're going to talk about multiple roots in a little bit. So that's the rule that we want to have now. So let's solve an example and see how we can apply this in real problems.
I have a question about g inverse y in there. It says G inverse y is equal to x, but why did you substitute it instead of y in the rule?
Which,
Yeah, this one.
okay, the probability of x is less than G inverse y.
Yeah, and G inverse y is x, right?
Yeah,
Then why G inverse of y came instead of y in the other row, the one above it?
this one?
Yeah.
So, okay, so maybe you missed that part. When we started, this is the function that is given in the problem, y equal to g of x, okay? So the thing is, we need to find fy, and we have a lot of information about x. Okay, so right now, everything right now in y, and we want to convert it to x. So we take out the y and substitute it with the function, gx.
Okay.
And then converted everything here to x's. Like you see, we started with a PDF of a random variable. The thing is, this is something like you have a load, and this load is x on a beam, right? And you want to find the reaction. So the reaction is going to be function of the load, like x squared plus 2x. So you want to find y as a function of x.
Okay.
So that's what we're trying to do. We substituted everything in x, like converted y, and then we put gx, and we had x alone.
But for the assigned value, is it y in there?
Where?
The assigned value.
Here?
No, next to it.
This one?
Yeah, the one above it, which is here, y.
Y? This is the small. This is the small y. Yeah. Yeah, this is y here.
Yeah, I mean, why it became G inverse y? Why is that? It says G inverse y is equal to x. Why you change it instead of y?
Okay. So the thing is, okay, let's say that you have a function y is equal to x squared plus 2x.
Okay.
And you know information, all the information about x. You have the PDF of the x, like I give you a load and I give you what is the distribution of this load on this beam. And the reaction of y is equal to x squared plus 2x, like function of the load. So the thing is, I need to remove all the y's and put x's. So g inverse of y means that you need to find the roots of this function, like you need to find what is the value of x. And let's make it much simpler by saying that y is equal to x squared. So x is equal to positive or negative y. That is actually the g inverse of y, which is x.
Oh, so they are the same?
Yeah, they are the same. Like,
Okay, I see.
so the thing is, what I did here, I take the inverse of both sides. So basically, you like, okay, I'm gonna put it like an example, and you're gonna figure out how this is working. I'm gonna put actual equation, and we're gonna drive this equation. Right, so let's say that we have this example. And right now, I'm not giving you y as equal to g, I'm giving y equal to ax plus b, a linear function, okay? Equation of a line. And if you draw this equation, so you're gonna have x, and here's y. And this is gonna be a line that has a slope. The intercept is gonna be b. And this line is going to be something like this, and the slope of this line is going to be a, and this is 1, right? This is the equation of this line. And what I'm asking you here, I want you to find out what is the BDF of y. Find the BDF of y, like find Fy of y. So we are gonna follow this rule, like Fy of y is gonna be equal to Fx of G inverse y. By the way, like G inverse y, I told you it's the same like x. So actually I can write this Fy equal to Fx, G inverse y is equal to x of x multiplied by dx dy. That is our rule. So Fy, that's the random variable that we want to find the BDF for. You already have x, and right now all what you want to find out is the dx dy. So I'm going to use the same rule. dx dy. So dx of dy, like you have already y is equal to ax plus b. Can you guys find what is dx dy is equal to? Of this function? Well, I have to differentiate with respect to y both sides. So if I differentiate with respect to y, this is gonna be 1,
1 by
and this is gonna be equal to
a
and
0.
not 0. No, it's gonna be when you differentiate ax d dy of ax is gonna be, this is constant, it's gonna be a, and it's gonna be a dx dy, right? If you are differentiated with respect to x, it's gonna be a, just a. So this is gonna be a dx dy, and when you differentiate b, it's gonna be 0, right? So you have to put dx dy.
Or you could just differentiate with x and just take inverse of it.
Yeah, you can do this. The thing is, okay, or you can actually
That's
do
what I
this.
did actually.
You can say that y, if y is equal to ax plus b, you can say that
dy by dt.
x equal to y minus b over a, and differentiate this with respect to y, so you're gonna have that dx dy is equal to 1 over a. So that's also another way to do it. So dx dy here, I'm gonna divide by a, so it's gonna be 1 over a. Same thing. All right, so if you wanna find fy is gonna be equal to fx of x multiplied by 1 over a. So that's what we are asking here in the problem. Or if you wanna take it from verse to principles, like, let's say, what we're trying to find. We're trying to find fy, like we try to find the BDF. Let's start with the CDF. What is the probability of y less than y? Okay, so this is equal to the probability. I know that y is equal to ax plus b, so I'm gonna substitute ax plus b here. And this should be less than y, right? And also, I can rearrange this. I can send b to the other side and divide over a, and this is gonna be the probability of x less than or equal y minus b over a, right? So it's the same thing. So that's actually what you didn't understand, like how we convert the function, how we convert it from function in y to function in x. So that's actually the g inverse of y, the image of your function y on the x-axis. So here is this probability, so that means we need to find out what is the f, that means this is the fx of y minus b over a. Okay, so, and this actually is the definition of fy of y. Since you have a variable x here, that means this is fx. If you have variable y, this means fy. And this is this variable, and this is this variable. So if you want to find out fy of y, you have to differentiate with respect to y. And same thing, since you differentiated the left-hand side with respect to y, you have to differentiate the right-hand side with respect to y. So, but this is fx. So what I'm gonna do, I'm gonna differentiate this with respect to y. Is gonna be the small fx y minus p over a multiplied by the differentiation of what is inside here with this function. So this should be dy of y minus b over a. So this is gonna be fx of y minus b over a multiplied by the derivative of this function with respect to y. B over a is gonna be 0, but y over a is gonna be 1 over a. So it's gonna give you the same thing like here. Fx of y minus b over a, like your function y is equal to ax plus b. So x is equal to y minus b over a. So that's basically fx of x multiplied by 1 over a, and that is what we are looking for. Is that more clear?
Yeah.
Yeah.
Okay. So rather than going, that's actually, I'm proving it. But in the exam or in the homework, you don't have to prove it. because we already proved it here, that fy of y equal to fx of x dx dy. I can use this function right away in one step. Two equations, but here, all what I explained the whole lecture, I did it again. Start sending things back and then arranging of variables until I came back to this conclusion, right? Okay, so that is,
And the graph there, the red one represents the relationship between x and y.
yeah,
And the blue one represents the probability of x happening or y happening.
exactly.
Okay.
So that's like, think about it like, as we said last time, that you have a beam, and this beam has a load B. B is the x. That's, you have a load on this beam and you know everything about this beam. You know the mean and the standard deviation, and you have the distribution, and you know what is the distribution of B, which is x. What we need to find out, what is the distribution of y? This thing.
Which is the reaction.
Which is like, for example, the reaction. The reaction here is B over 2. And let's say if you have a distributed load with it, so it's gonna be plus WL over 2. So you wanna find what is the reaction here. So the reaction here is y, is this function. Somehow you are gonna draw this function here. And then you will try to find what is the value of fy. Okay?
But the function in the red is the relationship between y and x, which
Exactly.
is the reaction of the load.
Which is the reaction, like maybe B is the random variable and W is but this is gonna be two random variables. So let's say it's only B. We're gonna talk about two random variables in a little bit, okay? All right, so what if the function is not monotonic? Like the function is not like only increasing. How about if it's increasing and decreasing? It's gonna be a little bit difficult. So let's see how we're gonna solve this. So let's say, suppose that gx is not monotonic. Like, let's say that our function is a parabolic. Like, for example, let me put here. This is the x-axis. And let's say my function is something like this, parabolic curve. And this is my y-axis.
Emergency notification system. This is only a test. This is a test of the FIU emergency notification system.
And
this is only a test.
And this is the distribution of
This
x.
is a test of the FIU emergency notification system. This is only a test.
All right, so this is our function. Can you guys tell me what is the function that we have here? Y equal x squared, right? Y equal to x squared. Why? Because this is at the center. It's not shifted up, it's not shifted down. So here y is equal to x squared. Here is a little bit different. How? Okay. So let's say that you have, this is your variable y. If at y you have two values of x, right? You have x here and you have x here, right? So let's call this x1. Let me write it up there. Or here, x1, and here's x2, right? Can you guys tell me what is the value of x1? Negative root y, right?
Yeah.
And what is the value of x2?
Positive.
Positive root y. So that's the two roots of the problem. Okay. So how did it come? Like you have to find the g inverse of y, which is gonna be that you need to find x. X is plus or minus root y. So you have a negative root and a positive root. So the probability that your random variable is less than y, that means that your probability here, put it in green. So you are looking for this part. So for y to be less than y, your x should be in between x1 and x2. If y, your random variable, goes beyond y, that means you went outside of this range. So right now we have fx of x is defined from negative infinity is more than less than infinity. So here we have negative infinity and here we have positive infinity or infinity. Okay, so if you want to find out the probability of y, right? You guys tell me, what is the probability of y is less than or equal to y? It's gonna be, so your y to be less than this random variable, the probability of your x random variable to be more than or equal to x1 and less than x2, right? And we can substitute, right now we have it as a function of x, we can substitute it as the g inverse. So this is gonna be the probability of your x to be more than negative root y and less than root y, right? So that's what we have here. You guys tell me, if I want to convert these probabilities, this is very easy. I can say that fy, y. But how can I do this as fx?
X is square root y minus.
It's gonna be the thing is, if I said fx2, that means that all this from negative infinity until x2. And if I said fx1, it's gonna be all this. So this probability is fx2 minus fx1. Because fx2 is the probability of x less than x2. It's gonna include this one. And fx1 is gonna include any random variable less than this part. So we can say that this is equal to fx2 minus fx1. Is that right? We discussed this last time. Like we had something, like we had a distribution like this, and we had A, and we had B, and if we want to find the probability here, this is going to be the fx of B minus the fx of A, right? Because the fx of B is all this part. And the fx of A is all this part. And if we want to find just this part, so it's going to be all this minus this. Okay. All right, so we can actually say that this is the fx of positive root y minus the fx of negative root y.
Professor, line about that? P of root minus y, P of minus
This line?
Line below that.
This one?
Yes, instead of x it should be y.
This one?
Yes, because it is the g inverse.
No, this is supposed to be x. Okay, so you have it here. This is the probability of x, like your random variable. Here is my random variable x. X is less than the negative root y and positive root y, which is equal to x1. So this is supposed to be x because this is fx. If this is y, this is never going to be f. X is going to be fy. And that's actually the point. We need to make the fy as a function of fx. Okay? All right, so so here what we want to do is we want to find fy of y. And to do this, I need to differentiate the fy of y. So I'm gonna differentiate both sides. So when I differentiate both sides, it's gonna be fy of y. So this is gonna be small, and this also, when I differentiate it, is gonna be small. So when you differentiate fx of root y, this is gonna be fx is small, of still root y, multiplied by the derivative of root y. Do you guys know the derivative of the roots? Like if you have 1 over 2 the roots, right? So it's gonna, this is gonna be 1 over 2 root y multiplied by dy dy. So I already differentiated with respect to dy. What is the rate of exchange of y with respect to y is 1. Okay. So I can't like keep it like this. Let's differentiate here. This is minus the fx of negative root y multiplied by the derivative of negative root y. It's going to be the same thing, negative 1 over 2 root y. So this is going to be fx of root y multiplied by 1 over 2 root y. Negative negative is going to be plus fx of negative root y multiplied by 1 over 2 root y. So this is going to give us a general solution that if you want to find fy from a function that has multiple roots, this is going to be fy of y is going to be equal to fx of x1 multiplied by dx1 dy plus fx of x2 multiplied by dx2 of the y, and that's what happened here. We have this is the root number 1, x1, and this is x2. By the way, if you see I interchange between the g inverse of x and x, the g inverse of y and x, so they are the same thing. So I know you might have got confused here, but if you want to write it as the g inverse of y or something, it's going to be the same thing. Okay, so what if you have a multiple roots, like not only 2 roots, like let's say that your function is something like this, and this is y, and this is x. Can you guys tell me this function, how many roots does it have? There's 1, 2, 3, 4, and 5. There's 5 roots. So the general function of the multi-roots problem is going to be, if you want to find fy of y is equal to the summation from I equal to 1 up to n, where n is the number of roots, multiplied by fx of xi dxi dy. And this is the general equation, okay? If you have multiple roots. Is that clear? I know it's a lot of information, but if you think about it, what we did today is only trying to find the BDF of functions of random variable. Like we said, if we have a beam, and this beam has a load, and this load has a function, either it's monotonic or non-monotonic. So that's the equation that we have. If this function have only 1 root, so like you remove the summation, so fx of xi or x1 dx dy. That's the general equation that we have. If you have a single root, so you are gonna only have 1 term, which is gonna be this one. If you have 2 roots, you are gonna have 2 terms, term number 1 and term number 3. If you have multiple roots, so you are gonna expand this fx is 3 multiplied by dx is 3 dy, fx 4 multiplied by dx f4 dy. So that's the last 40 minutes. We have been trying to prove this and do 2 applications on this. One is a linear, one is a variable, okay? All right, so let's move forward to one function of 2 random variables. Everything that we have done here, this function y is only 1 random variable, okay? So what if it's 2 random variables? Like your function is have a function in x and a function of y, and you have z equal to 5y plus 3x. Okay? So let's see.
Professor,
Hmm.
what would be a good example of non-monotonic function in our applications?
That's a good question. Okay, so we talked about a beam has a load, and okay, like for example, your load is triangle. When your load is triangle, your reaction is not gonna be function of W, maybe it's function of W squared or something. So, or you're looking for the bending moment. So for the bending moment that comes from a distributed load, constant distributed load, like let's say that you have a beam had 2 ton per meter squared over the length of the beam. If you want to find the bending moment is a random variable, the same way that the reaction is. The bending moment is WL squared over 8. So it's still like function of W, which is still constant. I'm not sure if you guys have something in mind that you have your function is function of something squared.
What about EI not constant?
Hmm?
EI not constant? What the function?
Well, we are looking, yeah, there's a lot of random variables, but we are looking for a random variable that is gonna have 2 roots, like 2 values. I mean, but maybe it's not in our application. I mean, maybe in other applications. By the way, many of these stuff we are not gonna use it. Like, okay, let me tell you something. All this stuff, maybe I haven't used any of these till now. What I'm gonna say in about 10 minutes, we're gonna use it. Like, it's gonna be very, very important. But maybe in other applications, like in physics applications, math applications. I believe maybe you have something in your homework that has 2 variables. Okay, so let's now talk about one function of 2 random variables. Okay, so right now when we talk about all this stuff, we said that y is equal to x. X is still one random variable. Even if x is equal to x squared, that's still one random variable, not 2 random variables, only one. What if your function is z equal to gxy, function of 2 random variables, x and y? How is this can be possible? Like, let's say this is your x and this is your y, and your function is something like this, like a circle or a specific domain V, something like this. This is your function gx, y. It can be a circle. Do you guys know the equation of the circle? X squared plus y squared equal to r squared, something like this. And I believe maybe in the homework you have a circle equation. So okay, z equal to gxy. What is the PDF of z? What we are looking for, what is the PDF of z? F z of z. By the way, imagine this. Right now, what I'm gonna do is the PDF of x and y. So let's say that we have x here and we have y here, and this is f xy. Do you guys remember when we have jointly distributed random variables? Right now, our distribution is not like this, it's like a hat. It's gonna be something trying to like make something like this. And your surface is somewhere here. G, X, Y, your circle somewhere here. And you are looking for the probability that this, like F, Z, of Z, that means that you want to find the volume, not the area. Under this, like you have your hat here and your surface area somewhere here. It doesn't cover your entire distribution. You're only looking for a surface area here. So you need to find what is the volume under these surface. Like what is the distribution under these surface. So before, it was like here. Not volume, it was like you have your distribution here and you just want to find this area. But right now you have two variables, and right now the area that starts to be volumes. Okay? All right, so let's see how we can find this. From Versal principles, we know if we want to find the probability of Z capital to be less than Z, which is our random variable to be less than a specific variable, that means I can substitute with D, this Z, GXY to be less than or equal to Z. So what does that mean if you guys go back to the joint probability? This means FZ of Z, and this is the integration over the domain B. This, like, let's say this is a domain B of gxy, which is a function of fxy, like gxy, fxy of x and y, dx, dy. So the thing is, as I said here, this is the fxy. If you integrated the domain or the volume under the gxy, like if you integrate over this surface is your fxy of x and y. Okay, it's a surface, right? It's function x and function y, and you get a value z. And if you integrated the volume under this domain, is gonna give you the fz of z. Okay. All right. So let's see this in an example. So our example here says that z is equal to x plus y. So x and y both are linear. So if you want to plot x with y, so it's gonna be, this is x and this is y. And you will find out that it's gonna be something like this. That's how the equation of this is going to be a surface equation. Like you have the z out of x-axis. So we're going to have a line like this. And what I'm asking you for, find the CDF of z. Fz of z. All right, so let's find this from what we learned here. So I put here fz of z, and I put here domain because I'm not sure if it's linear or if it's whatever the domain is, from negative infinity to infinity, if it's bounded, so I put a general domain. But right now, if you want to find the probability of fz of z, that means that you need to find, that means you want to find the probability of z, capital less than z, which means the probability of x plus y less than z. So if you want to find this, that means, like, let's say that fxy is something like this, and your line is here, say. Something like this. So the thing is, you want to find the volume under this fxy distribution if x plus y is less than this value. So you want to find everything that less than value. Anything that is more than this, you are not interested in. So basically, this is your domain.
from everything here. Everything here is not included. Everything here is included. What is this area? Is the area that represents zx plus y, and anything below than x plus y. Okay, and what I want to find I want to find the volume under this surface. So this is going to be equal to, okay, can you guys tell me how can I find this area? I need to do double integration, right? Before we only do one integration because our areas function in one variable. Right now we have two variables. So if you guys remember in integration how we did this, you either take strip like this, and this is strip like from negative infinity up to this point, right? And you integrate this strip from negative infinity up to positive infinity. And you are bounded from negative infinity up to this point. This point is equal to, like if you find, right now this strip is an x-axis. So I want to find the image of this on the x-axis. So your x is equal to z minus y. So your strip from negative infinity up to x equal to z minus y. By the way, you can do it in a different way. Like you can do it like, let's say this, and this is your line, and you want to find this area. You can take your strip, something like this. And this strip will start from negative infinity up to this point at y. So if you want to find y, it's going to be z minus x. Here, up to this value of y. And you are going to integrate on x from negative infinity up to positive infinity. Either are right, like if you do it that way or that way. So let's put this into action. All right, so here I'm gonna write f z of z is gonna be equal to the double integration. By the way, let's focus on this, okay? So the integration over the y-axis, as I said, this is gonna be from negative infinity to positive infinity. I wanted this strip move from all the way at the negative to all the way at the positive. So from the negative infinity to the positive infinity. How about the other way? The other way I'm gonna integrate from negative infinity up to this point. I wanted this line to stop my integration. So it's gonna be x, which x is equal to z minus y. And I'm integrating this function fxy of xy dx dy. So the thing is, I can substitute, like if I want to make this one single integration, like the way that I'm doing, I just want to make this strip to move from here to here, I can substitute with the boundaries here in this function. So once you integrate this with respect to these boundary condition, you are going to have this as a function of fxy, and let's substitute with x is going to be z minus y of y dx dy. So once you integrated once, the first integration, this function, you are going to put z minus y as a boundary of the integration, and then you do the last integration from negative infinity to infinity. Same way, if you did this strip, this is just an alternative solution. Like you can stop here, but you can also say that fz of z is equal to the double integration from negative infinity. Let's look at the y direction. So the y direction right now is from negative infinity up to z minus x. The x direction is from negative infinity to positive infinity. And here you are going to have fxy of x and y dx dy. And once you integrate with respect to x, you are going to have all this function, like you substitute in the, this is the y, sorry. This is the x. So you are going to substitute with y. So you are going to have fxy, and this is going to be z minus x I have to put here only y, because right now we integrated with respect to x, so we are only gonna be left here with y, the integration of y. Here, I integrated in the y direction, so I'm gonna here left with x. So if you have two random variables, this is gonna be the solution. All right? Well, it's a lot of integration, but once you go and focus and look at the graphs and look at the boundaries of the integration, you will find that all this makes sense. And as I said, you guys know fxy is the joint probability of x and y, this curve, right? But what is f and x are independent, like has nothing to do with each other. Do you guys remember? Like what if x and y are independent? Do you guys remember what is the fxy of x and y? It was f of x multiplied by fy of y, right? The probability of x multiplied by the probability of y if they are independent. So, like, if we want to substitute this here, like if they are independent, like let's look at fz of z. Just if this is going to be equal to, look at this function, it's going to be the integration from negative infinity to infinity, fx of x multiplied by fy of z minus x dx, which is, this is fy of y, like if you want to substitute with this z minus x, this is y. We just put the inverse of it, so those are okay. All right, the last thing that I want to discuss with you is what if your boundaries have a limit, like it's not from negative infinity to positive infinity, like let's say that I told you I'm only looking for x is more than or equal 0 and y is more than or equal 0. And your line, it's the same function, z equal x plus y. So you are not interested in everything that is negative. You're only interested in x more than 0 and y more than 0. So you're only interested from here. So your boundaries is going to change. Not from negative infinity, it's going to be from 0. All right? And you are not looking for all up to the infinity. You are looking when your variable is reached, like let's say that you have your strip here. Rather than having your strip is all the way to the end, no, this strip is going to be stopped here. It's going to start from 0 until it reaches this value, which is, this is the value of x, which is z minus y, okay? And this strip is going to start from, not from negative infinity, this strip is going to be from 0 until it reaches this value, and this value is at x equals 0. So basically, z here is equal to y at this point, because z is equal to x plus y, and here is x is equal to 0, so z equal x plus y, and x is equal to 0, so z is equal to y. So basically, you want to integrate this strip from 0 to z minus y, and from 0 to z, okay? So this is basically z, and here is z minus y, and you want to integrate the fx y of xy dx dy, and if they are independent, let's assume they are this plus independent variables. So this is going to be the double integration of fx of x, fy of y, dx dy, and right now you have the integration from 0 to z and from 0 to z minus y. So basically, if you integrated this strip first and substitute with, by the way, tell me, this integration is integrating in the y direction or the x direction? You have two integrations. You want to cover a surface. You cover the surface in x and cover the surface in y. From 0 to z, cover in y, and from 0 to c minus y is this strip. This strip covered the x-axis, okay? So this can be like, I can put the same boundaries, 0z and 0z minus y. So if you did your reverse integration, the second if you did this, and this is the one that integrates over x, and you're gonna have fx of z minus y, fy of y, and this is gonna be integration over dy. Okay, so this is how you to do the double integration. You finish the integration in the x direction first, and then do the second integration in the y direction.
Actually, in here, in the x direction, it should intercept also with y. Like,
Where? This?
yeah, the horizontal strip.
This horizontal strip.
It should intercept with y, which is,
This one, like you
Not
want to
this
say
one.
from here to here, right?
yeah.
Here actually is the 0, because this strip is in the x direction.
Okay.
So this strip is start from 0x and end at this line,
Yeah, which is z equal.
which is z minus y.
No, it should be z equal to x because all y here is.
Because this
y
strip
is-
moving, it's not constant.
But y gonna be 0 when it's.
Y is gonna be 0 if this strip is here. But this strip is variable, it can be any place. That's why we put it in a general location.
Then
Okay.
why we didn't do the same thing with the other one?
The other one is different. Okay, so the strip has a variable length, okay? And it moves from here to here. So here, the strip was z minus y and was equal to z when it's here.
Yeah.
But the thing is, this strip is our variable, and it keeps moving, because the thing is, you need your strip, the integration to cover all this area. So here, it was z minus y, it was z, and here your y is equal to 1, it was z minus 1, z minus 2, z minus 3, until you reach the value where z is equal to y.
And same thing happened in the vertical. Start from z equal.
We don't integrate that way. This is our strip. Our strip is having this length, and this length is variables, and it moves that way. If you want to integrate that way, your strip, if you want to integrate that way, your strip is going to be something like this. Say, like this, and your strip is going to be something like this.
Okay.
And here, this is going to be z minus x.
So we take only one strip and we bound it by the area. That
Yeah,
we
it's
have.
only one strip.
Okay, I thought we take
No,
this
two
on the
strips.
direction.
No, actually, when I did these two strips, that was a solution, and that was
Yeah.
another solution. Like,
Okay.
it's not the same solution. Like, you either big this way or big this way. The thing is, we need to integrate the area. So to integrate the area, we take one strip, and we do it all over the domain.
I see.
This strip can be x-axis, can be y-axis.
And we did here the highest domain in the vertical direction, which is z equal to y.
Z equal to y.
Yeah, I see now.
Okay. Right, so that's actually a lot of integration, a lot of stuff, a lot of loads to throw on you, but like if you go revise your integration and your double integration principles, you'll find that all this makes sense, like integrating a strip. And what we are doing right now, like when you have two random variables, it's gonna be really difficult, but if you understand this concept very well, it can help you a lot in your research, because we have a lot of many random variables that are interdependent on each other. Like, look at the, I'm not sure if you guys did some research in a storm surge and wave. Storm surge and wave are interconnected together. Two loads, like, okay, let's say this is how the hurricane like make landfall to the from the ocean to the community. So you will never have waves without storm surge. Like waves, it needs water below it so it can make the wave. Let's say that the storm surge is 0.5 meter depth. You will never get 3 meter wave height with 0.5 meter water depth. there's always, the wave is less than the storm surge. So there is
there is a connection between them. So they are interdependent on each other. So if you want to find a probability of damage that coming from a storm surge and waves, you need to find what is the relationship between these two random variables. There's definitely an equation that can connect them. Yeah, maybe it's empirical, but it's an equation that you can use to find what is the probability of something happen if these two variables happen. So first, you need a distribution of both of them. Like you need to have the storm surge on the x-axis and the wave on the y-axis and find what is the joint probability of both of them. And if you want to find at a specific, like let's say that the storm surge and wave are very, very low, so there's no damage that's going to happen. So if you're only looking for areas that doesn't have damage, so let's say it is this surface. So basically you integrate the area under this curve, which has the probability of both events happening together. Okay, so that can be an example of two random variables that are, and by the way, they are dependent on each other. They are not independent. Okay, like as I said, like if they are independent, it has nothing to do with each other. But actually, the wave height is connected with the surge height. The surge height, and it never exceed the surge height. There's usually, like it says, that the wave height should be less than 0.5 of the surge height. Okay. All right, so maybe I'm gonna use this 5 minutes just to introduce what I'm gonna do next lecture. So the thing is to do all this, like to do all this, all this analysis, and to have a distribution of x and y, you need to have a lot of data about x and y. So the thing is, and if you have a lot of data about x and y, you need some tools to discretize this data, like to model this data. Like the thing is to understand this data, like if let's say I give you an Excel sheet that has millions of numbers about the storm surge. You're not gonna look at these million numbers, it's gonna take forever to look at them. All what you're gonna do, you're gonna maybe use Excel to find me the average of this number and find me the standard deviation of this number. So there's tools, statistical tools that we use to like describe this data. And what I'm gonna show it to you right now, something is called numerical descriptors of random variables. Numerical descriptors of random variables. So what is the numerical descriptors of random variables? When you have a random variable, I mean like variable that you don't know. All what you have is a bunch of data, and this data has a million number, and your random variable may be one of these numbers. You don't know, okay? So how to describe a random variable? First, we need to know what is the most likely value. Most likely value. Like let's say Miami Beach, and I give you the tide or the storm surge height or the wave height, and I give you a million number of the wave height that happened over the last 50 or 100 years. Okay, so what you want to find out, what is the most likely value of the storm surge or the wave height that is going to happen at this location. Okay, so there's a descriptor of the random variable is called what is the most likely value. So the second descriptor is called dispersion. Okay, so that is the two main descriptors. So let's see what these descriptors tell us. The most likely value measure the central tendency. Dispersion measure the variation. Okay, so let's see what is the tools that we use to know what is the most likely value and what is the tools that we use to know the dispersion. So to know the most likely value, there's three tools that we can use to know that. The first tool is called mean
The second tool is called median. The third tool is called mode. Dispersion, the first tool that we have, it's called variance. Second tool is called standard deviation. The third tool, it's called the coefficient of variation. Do you remember when in the first lecture when I told you if we have a beam, I know what is the mean and what is the standard deviation? That's how we describe the random variable. But there's a lot of other ways that we can describe the random variable with. Maybe we can describe it other than the mean. I can use the median, I can use the mode. Rather than using the standard deviation, I can use the variance, I can use the coefficient of variation. So basically, the mean is the average of the data sets. If I give you a data sets, you basically take all of them and sum them and divide on the number of the data. Okay, so that's the mean is the average of the data set. The median is the number that is split the data into two halves. Like I give you a random data, so you are gonna arrange them from the lowest to the biggest, or from the biggest to the lowest, and come to the number that divide them into two halves. Okay, we're gonna talk about this. We're gonna give an example next time, but I'm gonna give you an idea. The mode is the value in a data set that is repeated most often. Like let's say I give you a data and the most repeated number is 10. So that's also a way to measure the central tendency, or how this data, or what is the central of this data, or what is the most likely value. So the most likely value is the value that happened most often. So mode is also a way to know what is the most likely values, to know what is the number that is repeated most often. Dispersion is, see how's the data like, okay, like for example, I give you a bunch of data, something like this. Dispersion is to see how's your data is distributed around the mean. Like let's say this is our mean, or this is our mode, or our median, and how this data is distributed around this mean. Like is your distribution something like this, or actually something like this, or something like this? How's this like the data set is around around their mean, okay? And there's a function, I'm gonna put it next time, how we can find the variance. Basically, the standard deviation is the root of the variance. Like the variance is like sigma square, and the standard deviation is the root of the sigma square is gonna be sigma. Coefficient of variation, basically, I'm gonna do this in detail next time. The COV is basically the sigma over mu. Like the standard deviation over the mean of the sample. We are gonna do this in details next time, but random variables needs descriptors. Like I can say a random variable has one single number. It needs something to describe it. So this is the two things that we can describe: the most likely value and the dispersion. And we usually use the mean and the standard deviation. However, sometimes we use the coefficient of variation if we have multiple data sets. So to compare the multiple data sets, we divide the sigma of the data set, the same data set, over its mean, and then like, let's say the wind equation has lots of k's. The wind load, and has q's, and has a lot of things. Everyone is random variable. So rather than putting two numbers to describe one random variable, we're gonna use one number to describe each one. And this number is the sigma over mu. All right, see you guys next time. We're gonna go through this in details with example to know what is the descriptors of random variable.